Imagine if the universe wasn't built from tiny solid particles, but from strange possibilities that only become real when measured. That sounds like science fiction, but in the past few years, physicists have uncovered discoveries so bizarre that even experts are questioning some of the deepest assumptions about reality itself. One experiment has pushed quantum behavior into larger and larger objects. Another has captured entirely new quantum states that were once considered impossible to observe. And perhaps most astonishing of all, researchers are now building machines that don't just calculate faster, they exploit the weirdest rules in nature to solve problems beyond the reach of today's most powerful supercomputers. These aren't theories from a movie, they're real scientific breakthroughs happening right now. And by the end of this documentary, you'll understand why many physicists believe we're entering the most important era of quantum science since the birth of quantum mechanics over a century ago. For decades, quantum physics has been famous for one unsettling idea. At the smallest scales, particles don't behave like tiny billiard balls. Instead, they exist as probabilities, spreading across multiple possible states until an interaction forces a definite outcome. Albert Einstein famously disliked this idea, calling it spooky. Yet experiment after experiment has confirmed that the quantum world refuses to obey common sense. Recently, scientists have begun exploring that world with tools far more powerful than ever before. Instead of simply observing quantum effects, they can now control them with astonishing precision. That change is transforming physics. One of the biggest breakthroughs came from quantum computers. Traditional computers store information as bits, either 0 or 1. Quantum computers use qubits. A qubit can exist in a superposition, representing multiple possibilities simultaneously until measured. Keeping qubits stable has always been the greatest challenge because even tiny vibrations or heat can destroy their fragile quantum state. But researchers have recently demonstrated dramatic improvements in error correction. Instead of watching quantum information disappear within moments, scientists are now preserving complex quantum calculations for much longer than ever before. This doesn't mean quantum computers are replacing laptops tomorrow, but it does mean researchers are crossing a threshold many thought would take decades longer to reach. For the first time, reliable quantum computation is beginning to look practical. At nearly the same time, another discovery shocked physicists. Researchers created increasingly complex quantum entanglement across larger systems. Entanglement links particles so deeply that measuring one instantly determines the state of another, regardless of the distance between them. This strange connection has been verified repeatedly. Recent experiments have expanded both the number of entangled particles and the precision with which scientists can manipulate them. Every improvement allows physicists to test quantum theory under conditions that were impossible only a few years ago. The results continue pointing in the same direction. Nature behaves far more strangely than everyday experience suggests. Then came another milestone. Scientists have become remarkably successful at controlling individual atoms using lasers and ultra-cold temperatures. These atoms can be arranged almost like microscopic building blocks. Instead of studying random quantum behavior, researchers now design entire artificial quantum systems from the ground up. This allows them to simulate materials that don't naturally exist on Earth. Some of these simulations may eventually lead to better superconductors, more efficient batteries, and revolutionary new technologies. But there's another reason these experiments matter. They allow scientists to ask a profound question. What happens when quantum effects grow larger and larger? Can the bizarre rules governing atoms eventually influence objects we can actually see? That mystery is driving some of the most exciting research happening today. Because recent experiments are beginning to blur the boundary between the quantum world and our familiar everyday reality. And what scientists discover next could completely reshape our understanding of the universe.
For more than a century, physicists have wondered where the quantum world ends and the classical world begins. Why do atoms behave so strangely, while baseballs, mountains, and planets appear perfectly ordinary? The answer has never been completely understood. Today, scientists are closer than ever to solving that mystery. Researchers are performing experiments with larger molecules, ultra-sensitive mechanical devices, and carefully isolated quantum systems that continue displaying quantum behavior under increasingly challenging conditions. Every successful experiment pushes the boundary a little further. Instead of finding a clear dividing line, physicists keep discovering that quantum mechanics survives far beyond where many once expected. That raises an extraordinary possibility. Perhaps the strange quantum rules aren't limited to the microscopic world at all. Perhaps they are the fundamental rules governing everything.
Another major breakthrough is happening in quantum sensing. By exploiting quantum effects such as superposition and entanglement, scientists are building sensors of incredible precision. These devices can detect unimaginably tiny changes in gravity, magnetic fields, and time itself. Quantum sensors could one day help map underground water, improve navigation where GPS cannot work, monitor earthquakes with greater sensitivity, and even search for new physics beyond the standard model. In laboratories around the world, these instruments are becoming practical tools, not just scientific demonstrations. Each improvement opens a new window into parts of nature that were previously invisible. Meanwhile, researchers are discovering entirely new quantum materials. Some materials allow electrons to move in unusual ways because of their quantum properties. Others display exotic phases of matter that challenge traditional theories. Understanding these materials could eventually transform energy transmission, electronics, and computing. Perhaps most exciting is the search for more stable qubits using topological quantum states. These states are naturally resistant to many types of errors, making them attractive for future quantum computers. Although this field remains under active investigation, steady experimental progress continues to bring these ideas closer to reality.